Thank you very much. I'm Jeroen van Hinnen. And as Sarah said, I give this talk on behalf of Alexandra or Ali Sweeney, who unfortunately couldn't make it today. Ali's PhD is looking into mine water heating, and this particular project that I will present today is on the thermal interference between mine water geothermal systems. So just to be clear, the kind of geothermal system that Ali has looked at was the one with an abstraction well and a reinjection well, which is different from the system shown on the left, which is a closed loop system, and the system on the right, which only has an abstraction well and discharges water into surface waters. The rationale for doing this is that if we want to effectively make use of all the heat that's available in the mines, we probably need more than the number of systems that we have available now. That means that systems might actually be located closely to each other and perhaps extracting heat from the one and the same mine block. So the mine blocks are shown in the plot on the right. And as Florna already introduced earlier today, we already have a situation where two systems are related fairly close to each other in Gateshead, where some system has been already set up by Lanchester Wines, and then last year Gateshead Council introduced a second scheme. They're only a few kilometers apart. And the question is how much interaction does happen between these schemes. So to address that, we Ali did some numerical modeling using the GEMS Toolbox software. This is kind of software, open source software that we developed at Turnham University. And the details about this software and the code itself are available through the paper listed at the bottom by Molly Castillo, or you can ask myself or Julian. Molly Castillo is here in the audience as well. The model we set up is a generic one to kind of come up with a more general recommendation of how regulation could be done. So we're not actually looking into individual geometries of specific mine systems. So the model setup is shown here in the plot on the right. Fairly simple model, 2 by 2 kilometers, 2 seams, using the wooden pellet type of coal extraction that leads to galleries. We modeled 2 different systems. One was where there's only one mine water system available, so that is has an injection point 1, where water is injected into the top seam, then it flows through the central shaft, which is shown in the middle of the plot. Water flows down into the bottom seam and then is abstracted at abstraction point 1. The second scenario we looked into is by adding a second user. So that is injection in abstraction point 2. And then what you can do is to kind of compare the two, one system and 2 systems, and see how much difference there is and how much interaction there therefore is between these users. It turned out that the most important parameters in this system is flow rate, so the pumping rate of each of the systems, the operation time, so the duration of the systems, and the distance that the water has to travel. So we'll look into these in a little bit more detail. So one particular model result shown here, where we have 2 systems available. Water is injected in the top seam at a temperature of about 10 degrees. The bottom seam has a temperature of 16 degrees, so that's the maximum that the water can warm up. As the water flows from the injection point through the shaft to the bottom seam, it warms up, in this particular example, to about 14 degrees. So it's not optimal, and it is partly due to the interaction between the 2 seams. Now, we did lots of different calculations, and fit varying parameters that I mentioned earlier, and then you start to see a pattern. So for example, here, this particular plot on the left shows what happens if you change the distance that the water has to travel. So in this case, the distance shown here is the distance between the injection point and the shaft. And as you increase that length, as you probably can imagine, then the water can travel for longer, has more time to warm up, so the actual abstraction temperature then increases. And that's shown with the line that increases from left to right as the distance increases. The axis on the left shows how much the water then increases from its injection temperature to its abstraction temperature. The red line is the situation if you have only one system to deal with. The blue line is if you add that second system to it. And as you can see, the blue lines below the red lines are in all cases the temperature for that second scheme, if you add that second scheme, is dropping. So the second scheme interferes with the first one to some extent. The big blue dot is the situation, the example I gave you in the previous slide. Now, a way to quantify how much interaction there actually is can be done through a parameter we defined that we call the heat extraction ratio, which is shown at the top of the slide. So it's essentially the amount of heat that each of the users would extract from the system if you have two users, divided by the amount of heat that only one user would have. So, and that ratio is somewhere between 0 and 1, so 0 and 100%. If it's 100%, it means adding user 2 doesn't do anything to user 1, so there's no interference whatsoever. 0 means there's maximum interference. If you add user 2, then user 1 doesn't get any heat at all anymore. So that's a useful quantity to kind of look at. Now, as I said, other parameters are important as well, not only distance, but also the flow rate, so the pumping rate, and the duration of the system in years. And that is shown here in this contour plot, with duration on the vertical axis and flow rate on the horizontal axis. And the optimal scenario where the heat extraction ratio is close to 1 is in the bottom left, so the yellow colors. And that is for small flow rates, so small pumping rates and small durations, which is probably what you'd expect. And there is very little interference. But as you increase the pumping rate or the duration, then the interference becomes more and more towards the top right of the plot, where there's most interference with large flow rates and large durations. Now, these results are probably fairly intuitive. This is kind of what you'd expect. But the nice thing is that you can quantify it using these models, and then you can use these quantifications to come up with a potential regulation for this. And one example is given here in the plot, which is referring back to the situation I showed you 2 slides earlier. So how the heat extraction ratio changes with the distance that the water is traveling. And what you can do is to set some kind of threshold value. So you'd say a threshold value of, in this particular example, the horizontal red line at 0.9, so 90%, which means that if you have one system and you start adding a second system to it, then you don't allow the amount of heat that user 1 gets to drop below 90%. If it's more than 90, if it gets below 90%, it's unacceptable. That's just an example. So if you would take that as a threshold, then you can look at the heat extraction ratio, which is the black line here, and see when it's above that 90%. And in this case, that's for a value of 679 meters. So that's 679 meters between the injection point and the central shaft. So if you remember the plot, the setup, that means that the distance between the 2 users is double that number. So it's roughly 1.3, 1.4 kilometers. So in other words, this kind of quantification gives you a tool to estimate what is the minimum distance that the users have to be apart in order to avoid too much interference. Now keep in mind that this is only valid for the flow rate of, in this case, 50 liters a second and a duration of 40 years. If you change these parameters, or if you change any of the other parameters that we use in the model, then obviously this number would change as well. So you'd have to look at this for individual cases, of course. Another way that this quantification can be useful is that in order to avoid having to do lots of these model calculations, you can actually come up with some kind of predictive equation that mimics all these model calculations. That's what we've tried to do as well. We used a multiple linear regression technique to kind of find a simple equation that kind of predicts, that mimics the results of all these models. And the equation is shown here at the top. And if you then try to match the values A, B, and C, then you can match the predictive equation, which is the curves in these plots, to the individual model calculations, which are all the symbols in here. And the fit is reasonable. It's not perfect, but it's probably enough. Of course, if you want this to be more accurate, then you'd have to come up with a more complicated equation. Finally, just to say that Ali also looked into the possible regulations that are already out there. There's not that much regulation yet for mine water heating because it's fairly new, but the three other industries that have actually quite a lot of regulation set up here are shown here. So it's oil and gas, ground source heat pumps, and geothermal. And particularly oil and gas has decades of regulations already set up. So we might learn quite a bit from that. And one of the things that is done in the oil and gas industry is that if there is too much interference between two systems, then they might be forced to unitize. So in other words, to merge the systems. And this might be something that could potentially work for mine water heat systems as well. Of course, heat doesn't travel as well as oil and gas, so that's something we have to keep in mind, but this is a potential option. So to conclude, modeling suggests that thermal interference between close-by mine water systems is enhanced by larger flow rates or more pumping, larger operation times, and shorter distances between systems. We might be able to use a concept called heat extraction ratio to quantify how much interference there is, and we can come up with a simple predictive equation to simplify this and without the need for further modeling. And finally, regulations could be borrowed from other industries that have already more experience with this. Thank you very much.